All right, thanks. Yes, so I'll be going through the first talk about the tools that we'll be seeing. So first, just to get set up, if you're using the Coffee Casa facility, I'll try to run on here as well. But any Jupyter notebook will work from the instance will work from the link that's in the agenda. So this is in workshops, AGC tools, foundation, and then there's a notebook called demo. So I'll be going through that. Okay. Yeah, so I didn't come up with the name for this talk, the foundation libraries, but I really like it because it really is the fundamental libraries that make up pretty much any analysis that's going to use all these tools is going to use the packages that I'm going to talk about here. So uproot, awkward array, vector, hist, mplhep. These are all packages that are part of the scikit-hep project, which is a collection of tools for hep data analysis, kind of like the foundational layer, the lowest layer for any analysis activity. So I'll go through briefly each of these parts of each of these and try to show how they work together. So most of this notebook is adapted from my Uproot tutorial, if you've seen that before, which is aimed at beginners in Python and data analysis. So here, I'm assuming that you're already familiar with at least Python, NumPy, and matplotlib, so it's much more compressed, and it covers more packages than that tutorial, and I've added a bit of more advanced tutorial, but it's still just scratching the surface of these packages, and so there are links at the end with more resources. Okay, so actually, so I see somebody's asking on Slido how you can pull the latest version. This is something that I had to do as well, so maybe I can just quickly go through that. So if you go to the Git little icon on the left, there's a pull latest changes button right here. So that worked for me for getting the latest version. But yeah, even if you're not using this facility, that's already set up, you can also just install all of these packages in your own environment with a simple pip install, and then all of these uproot, awkward, vector, hist, mplhep. These are the libraries that I'm talking about. They're also available with Conda on the Conda Forge channel. And then for importing things, so we'll use NumPy and matplotlib. So just importing those as usual, make the figures a little bigger by increasing the DPI. And then all of the scikit-hep packages that I'll be talking about can be imported like this. So most of them are just by their name. Awkward is usually imported as AK, and mplhep is usually imported as hep. And to kind of motivate going through these packages, I'll try to do a very short and simple analysis, if you want to call that I've done for the Uproot tutorial and for the previous AGC tools workshop, where I just have a CMS open data file that's in this repository. It's sitting in the same directory from proton-proton collisions in 2012. So it's a root file, and it just has information from muons. So the first thing you want to do is just start using these tools to understand how to open a file, see what's in it, and understand what kind of information there is. So in order to open a file in Uproot, you can just do uproot.open, and then this is the file that's sitting in this directory, open data example.root. So if I'll just restart the kernel to reset the numbers. So I'll run these in real time. All of these will be very short because this file is very small. Okay, so open this file and just store it in this variable here. So if you open a file in Uproot, you get a read-only directory object. So it's just saying that this is like a T directory if in root. And so if we want to see what's inside this file, just like any other kind of directory, you can list the contents. So in Uproot, the way to list the contents is with keys. So there's this file.keys function, which lists the objects, the keys that are in the file. So here there's one key called events. It doesn't say what type it is. It just says that there's this object called events, and then there's this cycle number, which you might be familiar with from root. And so, of course, root files can contain a lot of objects, including subdirectories. So if the objects that show up here when I do file.keys could also be directories, they could be histograms, they could be trees. So if we want to see what kinds of types there are in this file, we can do file.classnames. And then this shows now the names of the keys again, but also the types of the objects. So in this case, it shows that the events object here is a T tree. So this is the only object in this file. Okay, so then if we want to continue another level, so if we want to look at this T tree, we can access objects in the file with a notation like this, so like a dictionary notation. So just accessing this key called events, and then this is this T tree object that says it has 6 branches. So trees and root are basically just tables, so that where the columns of the table are the branches, and each row is an event, so individual bunch crossings. So we'll continue diving into each layer. So now we can look at this tree, just set it to this tree variable. Just gonna clear. I'm just going to clear the output so they don't show up. So then to look inside this the tree to see what kind of branches we have here, we can use keys again. So just like for the file. So if I say tree.keys, it shows the names of the branches. So there's these muon branches, n muon, and then PTA to phi, mass, and charge. And so this just shows the branch names. It doesn't show the types. There's also a function called show, which shows a nice little table with all of the names of the branches, the types, yeah, so here we can see that n muon is an unsigned integer, PTA to phi mass are basically vectors of floats. It's saying it's an array of floats for each event. And then charge is another, this is an array of integers for each event. So, okay, I have a few points in this notebook that are kind of asides for things that I'm not going to go into much detail on, but just things that are good to be aware of. Another option within the scikit-hep ecosystem for inspecting root files is this package called Uproot Browser. So this is another Python package that uses Uproot to provide a terminal interface similar to the T-browser graphical interface in root. So I have some screenshots here. I'll just bring up a terminal just to show it a bit interactively, just to see what it looks like. So if I do, so this Uproot browser can also be installed with just like pip. But then once it's installed, you can say Uproot browser, browse, and then you give it the name of the file. So in this case, open data example.root. And then this brings up, like I said, this T-browser kind of interface where it shows on the left side the name of the file and then any contents in here. So here it's showing events, which is a tree, then all of the branches that are in here. And then if I click on one of the branches like nmuon, then it will actually show a histogram of that branch, just like in T-browser. And so this is a kind of quick way that you can inspect a T-tree using these tools without having to actually use root. And also this is completely within the terminal. You don't have to open up any forward any X displays, which is nice. Okay. So then, okay, now continuing further down, now we have the tree. So let's say we want to get the actual data because we're trying to get to the analyze these dimuon events. So there are several ways to get the data out in Uproot. The simplest one is to just take the tree and say dot arrays. So for this simple example, this is fine for now. So then this outputs this array object, and so we can see the names of the branches in here, and muon pt, and then we can see the numbers, which are the actual data in the tree. So okay, I'll assign this array object to a variable called branches, and so now we can start looking at this object. So you can access a single branch from this branches object with a key kind of notation like this with brackets, and that'll give me this array that represents the nmuon branch. Or you can access it like a Python attribute, so say dot nmuon. This will give you the same thing. And so you can see this abbreviated list here of the number of muons in each event. So there's this ellipsis in the middle, so that it doesn't take up the whole page. You can see, so after the actual preview of the data here, it shows the type of this array. So it's saying that there are 100,000 entries of unsigned integers, 32-bit unsigned integers. And so we can look at the other branches, so say muon pt. So this branch has an entry for each muon, so it's a jagged array because the number of entries is different for different events. And we can see that there's an extra dimension because there are these brackets inside this list. So like this first set of brackets is just the muon pt for the first event. So there are 2 muons in the first event. And in the type string here, so it's still saying there are 100,000 entries, but each entry in the array has a variable length. So there's basically an array for each entry of floating point numbers. So this is a 2D array. It's an array of arrays. So these jagged arrays that we deal with all the time in HEP data, where there are different numbers of things in each event, different number of muons, different number of jets, are the primary reason for using awkward array over pure NumPy. Awkward array allows us to manipulate these jagged arrays in ways very similar to how NumPy can manipulate non-jagged or rectangular arrays. So if we want to focus on one particular event, we can index it just like any normal array. So I take this muon pt branch and just look at the first element, so the 0 element. And so this will show this array just for the first event. So it just has these two muon PT values. And yeah, it's not specified, but the units are GeV. This is a nano AOD like format. And so I can look at any of these other events within this array. So like the third event here only has one muon. So that's one dimension that we can look at. You can also just look at all of the information about a single event if we're trying to understand what events look like. So instead of indexing by the branch name or accessing by the branch name, we can just go straight to an index like 0 here to look at the first event. And so this, so now this outputs a record object. And okay, so there's a lot of things abbreviated here. You can also just look at, we can just look at the type of each, if we look at the type of these, we can do branches.type to see the full type for each event. In other words, all of the types of each branch from here. So this is showing there are 100,000 records. So this dictionary here shows all of the branch names and the types. And so each entry, like this 0th entry, has a type of basically this dictionary in here. So it's saying that there's a field called nmuon, that's this unsigned integer, and a field called muon pt. That's an array of floating point integers and so on. So in awkward, when you have different fields and they have names and types, this is called a record object. And so this is a type provided by awkward array, and it's basically like a Python dictionary, just with specific types for each field. And so most of the information, like I mentioned here, when I did branches subscript 0, most of this information is hidden just so that it doesn't take up a large amount of the page if there are many entries here. But one trick to just forcing printing all of the information, assuming you're looking at a small enough slice of the data, so in this case it's just one event, so we know it's okay, I can say .toList. So with any array or record, I can add toList, which is similar to NumPy. NumPy arrays have this function as well, and this will just convert to native Python types, so like dictionaries or lists as appropriate, in this case both. So this just converts to a dictionary with all of these branch names and their values for the first event. Okay, so next I'll start talking about histogramming. So histograms are a critical component of any analysis in high energy physics. So
there's a question.
So branches.nmuon is a type of high-level array. What's the difference to a normal AK.array? For example, the layout method behaves differently. Okay, so this is maybe a question for Jim.
Yeah, there's no difference. It's a synonym. Awk.array is precisely the same as awk.high-level array. I don't know how the layout method could be acting any differently.
I asked the question, and when I type, maybe it's not important, but when I type .layout, I either get like this XML string, or I get some other representation. It's just something I just noticed. But maybe we can take that offline.
Okay. yeah, I think we can go ahead then, but yeah, they're basically the same. Okay, so right, so for histogramming here, I'll be talking about hist, which uses the powerful boost histogram library for providing you can get quite complex types of histograms and types of axes, and it's very efficient. It's very high performance for filling large histograms. So hist provides the interface for defining histograms and filling them, and then generating the actual graphical plots of histograms is handled by mplhep and matplotlib. So mplhep is a package that extends matplotlib with several convenient features that are important for hep data analysis. So since we're looking for dimuon events, just for example, let's make a histogram of the number of muons in each event. So here we can make a histogram with this capital H hist, and then we just have to define the axes for the histogram that we want to, whatever axes we want to have bins on. So the simplest type of axis for hist is regular, so it's just regular spacing of bins, and so then you just say the number of bins and the low edge, the minimum and the maximum for the bin edges, and then I can define a label here, so I'm saying the number of muons in event. And then, in fact, maybe I'll split this so we can just define this histogram object, so this can be separated from the filling and plotting, and so this just shows what this histogram object actually is. And then so kind of similar to root, I can do h.fill and then give it the array for the number of muons. And then there are also many different ways that you can plot these histograms. The simplest is just to say dot plot. So separate this out as well. So first I can fill the histogram, and then if you're in a Jupyter notebook, there's this nice little representation that shows up even without using matplotlib. But then if we want to like customize a full plot, then we can use h.plot, and then I can just set like the y label. So this is now using matplotlib functions. So I can say h.plot, and then it gives me this histogram of the number of muons in each event. So we can see here that almost half of the events have 2 muons in the event. But then there are plenty with 0 or 1 or more than 2, and there's this tail going out. So then, okay, the next step would be manipulating the data for whatever analysis cuts and different parts of the analysis that we have. So uproot and awkward array are designed for columnar analysis, which is one of the big themes of the this whole ecosystem that we'll be talking about in this workshop. And so this means performing operations on entire columns or entire branches at a time, rather than operating on each event individually, like in a traditional event loop framework. So this shift can take some getting used to at first if you haven't done much of this before, but it's generally much more computationally efficient. And this is the same kind of approach that, for example, our data frame takes. Our data frame is also mostly a columnar approach. So the simplest thing that we can, a kind of analysis task that we can do after actually extrapolating or extracting the data is just counting things. So like a cut flow. So to count the number of total events, you can just use len, the built-in len on any of these, the the whole array of branches or any of the individual branches, and these will output 100,000. Or we also already saw it just from at least in the representation, it's also in this string here. But if we just want to get the number out, we can use len. Okay. It's like there's a question. So what's the main benefit of using hist over boost histogram directly? Yeah, so it looks like that's already been answered. So yeah, syntactic sugar and convenience, but hist and boost histogram are pretty closely tied. There's just, yeah, some more convenient functions that are available in hist.
Plotting. Boost histogram
yeah.
is really pure and doesn't have plotting.
Right. Okay. So yeah, so len will tell you only the length of the outermost dimension. So the muon PT branch has more than 100,000 numbers in it because there are, you know, an average of more than one muon per event. So we can see this by flattening the array. So we can use numpy.ravel. This is one option for totally flattening the array. So this is just removing the second dimension, removing the like inter-event or intra-event dimension. So this is just removing all of the boundaries between events and then just flattening all of the muon PT to a one-dimensional array. So we can see that there are like 235,000 muons in this file. So I've used a numpy function here, this numpy.ravel, on an awkward array. And so most of the standard numpy functions work fine on awkward arrays, but there are also equivalent functions within awkward. So you can also just say ak.ravel. In most cases, basically the default behavior between numpy and awkward for these functions that have the same name are the same, but the awkward versions have parameters that can extend the functionality that can extend the functionality to things that only make sense for jagged arrays. So one example is like ak.num, which counts the number of entries along in a particular dimension. So here the ak.num default is to count the number of well, actually, let me double check so I don't say something wrong. It's yeah, the default is axis equals 1. So the default is to count the number within each row. So in this case, if I do ak.num on this muon PT branch, it will count the number of muon PT entries for each event, and then it'll just provide those counts as an array. But as I just showed, there's a parameter called axis. So if you had more dimensions and you wanted to count along the number of entries along the second or the third axis, then there's a parameter for doing that. In NumPy, this doesn't make sense because the number would be the same for all entries because it would be rectangular. So you could, for a NumPy array, you can just do dot shape. And so this is kind of the equivalent for awkward arrays of like NumPy nd array dot shape. Right, okay, so now let's say we actually want to make some cuts, so some selections. So yeah, to pretty much anything we want to do, we'll be making some kind of selections. So one of the ways that we can make selections is by doing some kind of test, like whether something is less than or greater than or equal to. So one option is, let's say I could just look at make a cut on events with one muon. So I can say branches at muon equals 1. So this is now going to check the equality between each entry in this n muon branch against 1. So this is just like NumPy. We can take an array, make some comparison to a scalar value in this case, and then it gets broadcasted across across the array, so that we get the result of comparing each element to this number. So in this case, we can see that the false entries are where the number of muons is not, or is not 1, and then the true entries are where it is 1. So so this provides a mask that we can use to select only events that pass some selection. And so here I can set this mask. I can assign this to a variable. So I'll just say single muon mask equals this Boolean array here. So then if we want to know how many of these single muon events there are, then one way to do this is to just sum across this mask. So I can say numpy.sum single muon mask, and this will just add all the true, it'll convert the array to basically integers. So true is interpreted as 1 and false is interpreted as 0. So it just shows the number of true entries. So there are 13,000 plus events with exactly 1 muon. So this part is exactly like NumPy. And also like NumPy, if we want to apply this mask to one of these arrays, we can just use it as like a subscript. So we can just put it in like a slice or an index, just putting it in brackets for, say, if we want to get the muon PT entries, but only for events with exactly 1 muon, I can use this single muon mask, and then we can see that each one of these entries just has 1 muon PT. And then here it shows that they're the same number, 13,000 plus entries. So we've really just cut out all of the events that don't have exactly 1 muon. And then you can check this with len as well. So, okay, then now that we have selection, we can plot using these selections. So we can make another histogram, say this muon PT for only the single muon events. So I can just make another histogram like I did before, putting the label in for muon PT, and then fill the histogram. And so the only thing you have to be careful about is making sure that you flatten the array, since this still has more than one. This array still has more than 1 dimension. So I can just use NumPy or awkward.raffle to fill this histogram and then plot it, and then I get this nice histogram. And I just set the Y scale to log. Okay. So like I said, that's basically all like NumPy and not that different from matplotlib. If we want to do selections from jagged arrays, awkward array makes it almost exactly the same. So I can compare a jagged array or some function of a like manipulation of a jagged array to some number. So in this case, let's say I wanted to look at the muons that have an absolute value of eta less than 2, I can just make a mask like I did for the number of muons. So then this will output a jagged array of Boolean values. So this is just broadcasting across this like less than 2 absolute value, less than 2 comparison across all of the values, across all events, and all the muons within each event. So this has the same shape as the original muon eta array. And I can say count the number of values that the number of values, the number of muons with an absolute value of eta less than 2 by using numpy.sum, just like I did for events. So this works, numpy.sum works on jagged arrays. It'll just by default sum across all dimensions. And so this is the number of muons that pass this particular cut, 204 plus 1,000. And then for, so if I want to plot with this, these selections, it's basically exactly the same. I can make a histogram, now just changing the parameters here, the number of bins and the minimum and maximum values, and then filling with, say, this eta branch. So then just plotting without any selection on these eta values. And then, okay, here, I can even use the same hist object. I could make another one, or I could just reset. So this dot reset object just resets all of the bin counts, basically, so that I can fill it again. And so then I can just plot it again, but now applying this eta mask so that it's only plotting muons with an absolute value of eta less than 2. And so we can see that from this, the fact that there aren't any entries below -2 or above 2. One thing I'll just mention, since it's here and I don't have it in the notebook, this eta hist object, I can access a few different things from this. So like if I say axes, there's only one axis here, I can inspect the axes that are within this histogram, and I can get things like the bin edges. If I say dot edges on this, it'll show the edges of all the bins. There are things like centers. Centers. So I can access all of these things from this object. I can also access the counts of these bins. So I can say like access the count of the first bin, which is at -2.5, so there aren't any from this histogram, so the entry is 0. You can index by the bin numbers, or you can also index by the actual like value if you want to get a bin at a particular value on that axis. So say I wanted to get the bin counts at the bin that's at like eta equals 0. You can do this with a little trick where you make it a complex number, and then so if you had this j, it makes the Python complex number, but then whatever number is next to here, it'll look for the bin at that actual value on the axis. So this is looking at the bin content at the bin that's sitting at an eta of 0, and so it's 6,300. So that's
just as a reminder, we have about 8 minutes left, Mason.
Okay, yeah. Yeah, and so then we can operate on these selections by combining them, just like, again, with NumPy, there you can use all the Boolean operators like not, so there's like the tilde and or. So these just combine and broadcast just like NumPy arrays. So I can look at, say, events with exactly 1 muon, but only muons that have an absolute value of less than 2. And then, okay, another point on histograms. So if I want to say compare 2 histograms, plot 2 histograms on the same plot, one trick that we can do for this is to make a hist object with, so the kind of regular axis here with muon pt, and then if we want multiple categories, we can use this axis type called stir category, and so this will allow filling different categories. And so you can specify the categories here. You can also do this trick where you say growth equals true, and so this means that it'll, as you fill with new categories, it'll add the categories to this axis. And so then I can just fill this histogram with, say, different masks and just set the categories. So like first fill with muons with an absolute value of eta less than 2, and then fill a category with the inverse of that, so absolute value of eta greater than or equal to 2. And then I can plot that, and just like matplotlib, there's a parameter that's where you can say density equals true, so that histograms are normalized the same way. And so then here we can get histograms on the same plot showing the muon PT for these two different categories. Okay, so then so we're interested in dimuons, so dimuon events. So I just said another mask that looks for 2 muons in each event. Okay, so there's awkward array provides this very nice function where you can define behaviors for certain kinds of arrays. So you can define special like domain specific functionality, like for example 4-vector operations, so functions that can do things like delta R and 4-vector sums. You can define your own things with ak.behaviors. For 4 vectors, this already exists in a package called vector. So you can just, okay, vector was already imported, but so with vector you can just provide these branches for a 4-vector, and it'll create an array of 4 vectors. And then I can mask this by dimuon events. So only look at these 4 vectors for events with 2 muons. This is this momentum array for D. So this is the array of 4 vectors. You can access all of the usual components of these, like PT, eta, phi, pretty much any component you might want, not just the ones that we put in. And then if I want to, I can slice awkward arrays in multiple dimensions. So if I wanted to slice across all events and just get the first muon, I can do it with this, just this slice notation. So I can get the first muon in these events and the second muon. And then I can say get the delta R between them with just this delta R function. So then this shows the delta R between these 2 muons in each one of these events. Okay, I can plot it just like I did with all the other things. So just get a delta R plot. And like I said, vector implements 4-vector sums. So I can just add these 2 arrays of 4 vectors together to get the 4-vector sums for each event. And then for dimuon events, we want cases where these 2 muons have opposite charge. So I can just make a mask where these charges are opposite. And then that creates the final array that I need for dimuon 4 vectors. So this is the 4-vector sum of the 2 muons in events where they're exactly 2 muons and the signs are opposite. The sign of the charges is opposite. Sorry, this didn't have the. Oh no, I did. Yeah, no, that I forgot. This is duplicated. So this has already been. Ignore this part. It's already been done. So it's in this dimuon P4 variable, and so then I can again plot the mass of these 4 vectors exactly the same way as any of the other ones, except here I'm using another axis type for hist that's called variable. So this is just where you provide the edges of the bins. So here I'm just using log, like log spacing for the x bins. And then this creates this histogram here. And I'm using, there are different parameters for within matplotlib. Here I use hist plot, which provides this many different, well, several parameters for different types of histograms. So here just to show a different style of histogram, I can use this fill instead of the just the lines that were there before. And so this shows the the different resonances in these dimuon events. And Yeah, okay. I guess in the last couple minutes, I think I'll just mention some of the more advanced things. So Jim mentioned that arrays, I think in the Zoom chat, yeah, that arrays doesn't work if you have large files or lots of files. So there are other ways to deal with multiple files and large files. You can use uproot.concatenate. You can use iterate, which will just go by chunks of events, or you can specify just a certain number of events to look at with entry stop, or you can just look at individual branches. And there's also uproot.lazy, which does a similar thing to uproot.iterate. It looks at things in chunks, but just doesn't load. It provides an interface that's more like dot arrays. And then, yeah, okay, I don't have time to go through all of this, the last couple sections, but just saying that uproot can also create files, and you can create, arrays and vector new objects that weren't already in files, and so it provides a similar interface to root with things like recreate. You can create a new file and then write the arrays that you've created to trees, or write histograms. So like with this right here, I can just open this new file that I've created and assign this histogram, this histogram that I created to a key within this file, and now it's stored in that root file. And then I can, just to show the whole cycle, I can then open that file with uproot and recreate the plot. And then the last thing that I'll just mention is that awkward array supports numba, which is a library for just-in-time compilation for Python functions. So this is potentially very convenient if you have algorithms that are difficult to translate into fully columnar operations, because you can write the loops in Python, but then use numba, just a little decorator on the function, to get close to like native C++ performance. Okay, so just to conclude, there are a lot of powerful Python packages available for HEP data analysis. You'll hear in more detail about these and more of them throughout today and tomorrow. Obviously, I've only very briefly gone through some of the most popular ones. These packages roughly do these things, but of course they do significantly more complicated and detailed things as well. So at the end, I just provide a link to all of the GitHub repositories and the documentation for each. And in particular, there's some links to other presentations and tutorials, for example, in the awkward array repository. Okay.
Great. Thanks a lot, Mason, for this very nice tour through all of the foundation libraries in this ecosystem. We've had a few questions already throughout that you've addressed. If there's any last